On July 1, 2025, astronomers discovered something extraordinary racing through our solar system. A massive interstellar object designated 3I/Atlas that dwarfs all previous visitors from beyond our cosmic neighborhood. This colossal traveler, potentially up to 12 kilometers wide, is moving at over 150,000 miles per hour on a trajectory that confirms its origin from another star system. Unlike the mysterious Oumuamua or the smaller comet Borisov, 3I/Atlas represents our largest confirmed interstellar visitor, offering unprecedented opportunities to study material from distant worlds before it vanishes forever into the cosmic void. The historic discovery. What started as a routine night of sky surveillance on July 1, 2025, became one of the most significant astronomical discoveries of the decade. The Atlas Survey Telescope in Rio Hurtado, Chile, operated by the University of Hawaii as part of NASA's Planetary Defense Network, detected an unusual moving object approximately 670 million kilometers from the Sun. Initially catalogued as A11PI3Z, this faint dot immediately caught astronomers' attention due to its peculiar trajectory and unexpected brightness. The Asteroid Terrestrial Impact Last Alert System, known as ATLAS, consists of 4 telescopes strategically positioned across the globe. 2 in Hawaii, 1 in Chile, and 1 in South Africa. These automated sentinels continuously scan the night sky, photographing the same regions multiple times to detect moving objects that might pose threats to Earth. However, what they discovered on that July night was something far more extraordinary than a potentially hazardous asteroid. Confirming interstellar origins. The confirmation that 3I/Atlas originated from beyond our solar system required careful analysis of its orbital mechanics and trajectory. Unlike objects native to our cosmic neighborhood, which follow predictable elliptical paths around the Sun, interstellar objects travel on hyperbolic trajectories, essentially one-way tickets through our solar system. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, explained that the object's velocity and trajectory definitively prove its interstellar nature. When astronomers traced its path backward through space, they found it approaching from the general direction of the galactic center, though pinpointing its exact stellar origin remains impossible due to the vast distances and timescales involved. The object's designation as 3I/Atlas reflects its historic significance. The 3I indicates it's the third confirmed interstellar object ever discovered, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. The Atlas portion honors the survey system that first detected it, while its formal comet designation C/2025N1 indicates it was the first non-periodic comet discovered in the first half of July 2025. What makes this discovery particularly remarkable is the object's speed relative to the Sun, approximately 60 kilometers per second or about 134,000 miles per hour. This velocity is far too high for any object gravitationally bound to our solar system, providing conclusive evidence of its interstellar journey. Unprecedented size and characteristics. The sheer scale of 3I/Atlas sets it apart from all previous interstellar visitors. Current estimates suggest the object measures between 5 and 15 kilometers in diameter, making it potentially dozens of times larger than Oumuamua, which was only about 400 meters long. If confirmed at the upper end of these estimates, 3I/Atlas would be the largest interstellar object ever observed. Dr. Daryl Seligman, an astrophysicist at Michigan State University, who has been studying the object since its discovery, describes 3I/Atlas as shockingly bright despite its enormous distance from Earth. This brightness could indicate either exceptional size or an unusually reflective surface composition. The object's luminosity allows telescopes to observe it clearly even though it remains much farther from Earth than Oumuamua was when discovered. Early spectroscopic observations reveal that 3I/Atlas exhibits a reddish hue, similar to objects in the outer regions of our solar system. This coloration suggests the presence of organic compounds and complex hydrocarbons that have been altered by billions of years of cosmic radiation exposure. Perhaps most intriguingly, 3I/Atlas shows clear signs of cometary activity, including a faint coma, a hazy envelope of gas and dust surrounding the nucleus. This activity indicates the presence of volatile materials like water ice, carbon dioxide, and other compounds that sublimate when heated by solar radiation. Comparing the interstellar visitors. The discovery of 3I Atlas gives astronomers their third data point for understanding interstellar objects, and honestly, it reveals some fascinating diversity among these cosmic wanderers. Each visitor has exhibited unique characteristics that, well, really challenge our expectations about objects from beyond our solar system. Oumuamua, discovered back in October of 2017, is still the most enigmatic of the three. Its extremely elongated shape, lack of visible cometary activity, and that mysterious non-gravitational acceleration, these all sparked intense debate about what it really is. Comet 2Y Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, turned out to be more conventional in its behavior. This object clearly showed typical cometary characteristics, including a visible tail and a composition similar to comets in our own outer solar system. 3I Atlas, though, seems to bridge the gap between its predecessors while introducing a whole new set of mysteries. Like Borisov, it shows cometary activity, but its enormous size and those unusual brightness patterns definitely set it apart. Dr. Mark Norris from the University of Central Lancashire notes that 3I Atlas doesn't look like either of them, which is crazy and exciting. The rapid succession of these discoveries, 3 interstellar objects in less than a decade after centuries of seeing none, suggests, such visitors may be far more common than we ever thought. Advanced Observational Campaign. The astronomical community has really mobilized an unprecedented international effort to study 3Y Atlas before it disappears into the depths of space. Unlike Oumuamua, which was discovered as it was already leaving the solar system, 3I Atlas was detected early enough to allow extended observation campaigns using the world's most powerful telescopes. The James Webb Space Telescope, with its exceptional infrared sensitivity and massive 6.5-meter mirror, is perfectly positioned to analyze the object's composition and thermal properties. Webb's instruments can detect specific molecular signatures in the comet's coma and tail, potentially revealing the presence of water vapor, carbon monoxide, methane, and other volatiles that could provide clues about its origin. The Hubble Space Telescope continues to monitor 3I Atlas using its ultraviolet and visible light capabilities, complementing Webb's infrared observations. Together, these space-based observatories provide a comprehensive view across multiple wavelengths of light, revealing details impossible to obtain from ground-based telescopes alone. Ground-based observatories worldwide have also joined the effort. The Very Large Telescope in Chile, the Keck Observatory in Hawaii, and numerous other facilities are tracking the object's brightness variations, rotation, and spectroscopic properties. Radio telescopes, including the Very Large Array in New Mexico, are monitoring for any unusual emissions that might indicate unexpected activity or composition. This coordinated global effort, honestly, represents the most comprehensive study of an interstellar object ever attempted, taking advantage of technological capabilities that just weren't available during previous encounters. Ancient origins and cosmic age. Recent research suggests that 3I Atlas may be one of the oldest objects ever observed, potentially predating our solar system by billions of years. Dr. Jesse Hopkins and his colleagues at the University of Oxford have developed models indicating that this interstellar visitor likely formed around an ancient metal-poor star in the galaxy's thick disk, a population of stars that formed when the Milky Way was much younger. Professor Chris Lintott, co-author of the Oxford study and presenter of BBC's The Sky at Night, explains that there's approximately a 2/3 chance this comet is older than our 4.6 billion-year-old solar system. If confirmed, 3I Atlas would represent a pristine sample of materials from the early galaxy, preserved in the deep freeze of interstellar space for eons. The object's ancient origins could explain its unusual characteristics. Unlike comets in our solar system, which have been repeatedly heated during passages near the Sun, 3I Atlas may be experiencing its first encounter with stellar radiation in billions of years. This pristine nature could account for its unexpected brightness and activity patterns. Dr. Michelle Bannister from the University of Canterbury notes that the gases released as 3I Atlas is heated by the Sun will test theoretical models about ancient comet composition. This temporal perspective transforms 3I Atlas from merely an interstellar visitor into a potential time capsule from the galaxy's youth. Trajectory and future encounters. So, 3I/Atlas is currently following a precisely calculated path through our solar system that will bring it to perihelion, its closest approach to the Sun, around October 30th, 2025. At this point, it will be approximately 206 million kilometers from the Sun, just inside Mars's orbit, but still at a safe distance that poses no threat to Earth. The object's trajectory offers both opportunities and challenges for observation. During its closest solar approach, 3I/Atlas will be positioned on the opposite side of the Sun from Earth, limiting direct observation during its most active period. Dr. Astor Taylor, a graduate student in astrophysics at the University of Michigan, explains that despite the object's incredible speed, astronomers will have several months to study it. The comet will remain visible to large telescopes until early 2026, after which it will fade into the darkness of space, never to return. On October 3, 2025, 3I/Atlas will make its closest approach to Mars, providing an opportunity to measure how planetary gravity might subtly alter its trajectory. The object's outbound journey will take it beyond Jupiter's orbit by mid-2026, beyond Saturn by 2027, and eventually beyond the influence of our solar system entirely, resuming its eternal voyage through the galaxy. Scientific implications and astrobiology. The discovery and study of 3I/Atlas carries, honestly, some pretty profound implications for our understanding of planetary system formation, the distribution of organic materials throughout the galaxy, and potentially the origins of life itself. As the largest confirmed interstellar object, it offers an unprecedented opportunity to analyze material from another stellar system in detail. If spectroscopic analysis reveals complex organic compounds within 3I/Atlas, it would support theories that interstellar objects serve as vehicles for distributing the building blocks of life across the galaxy. This concept, known as panspermia, suggests that life's ingredients, or even life itself, might travel between star systems aboard comets and asteroids. The object's ancient age adds another dimension to its astrobiological significance. Materials preserved in 3I/Atlas for billions of years could contain information about the early galactic environment when the first generation of planets was forming. Dr. Rosemary Dorsey from the University of Helsinki emphasizes that studying 3I/Atlas provides insights into the role that ancient interstellar comets play in seeding star and planet formation across the galaxy. The object's composition and behavior could reveal whether the chemical ingredients necessary for life are common throughout the cosmos. The discovery also informs models of planetary system evolution, suggesting that the ejection of material into interstellar space is a common process that connects distant stellar systems through the exchange of matter and potentially biological information. Future detection and exploration. The discovery of 3I/Atlas comes at a pivotal moment in astronomy, as new survey telescopes prepare to, really revolutionize our ability to detect interstellar objects. The Vera C. Rubin Observatory, scheduled to begin operations soon, will photograph the entire visible sky every few nights, creating a comprehensive movie of the cosmos that should dramatically increase the rate of interstellar object discoveries. Predictions suggest that Rubin Observatory might detect between 5 and 50 interstellar objects during its 10-year survey, with some potentially as large as 3I/Atlas. The discovery also highlights the potential for rapid response missions to intercept future interstellar objects. While 3I/Atlas was detected too late for any spacecraft to reach it, several space agencies are developing concepts for high-speed interceptor missions that could be launched on short notice when the next visitor is discovered. The European Space Agency has proposed the Comet Interceptor mission, designed to study a pristine comet or potentially an interstellar object. NASA and other agencies are exploring similar concepts that could provide direct sampling and analysis capabilities, opening entirely new frontiers in space exploration. These future missions could answer fundamental questions about interstellar objects that remote observation cannot address, including their internal structure, precise composition, and the processes that ejected them from their home systems billions of years ago. A new era of cosmic discovery. The arrival of 3I/Atlas represents more than just another astronomical discovery. It marks humanity's entry into a new era of cosmic exploration where we can study material from distant star systems within our own solar system. Each interstellar visitor provides a unique window into the processes shaping planetary systems throughout the galaxy. As 3I/Atlas continues its journey through our cosmic neighborhood, it carries with it secrets from an ancient star system that may have died billions of years ago. The data collected during its brief visit will be analyzed for years to come, potentially reshaping our understanding of planetary formation, the distribution of life's ingredients, and our place in the galactic community. The rapid succession of interstellar discoveries, from Oumuamua to Borisov to 3Y Atlas, suggests that our solar system exists within a busy galactic highway where objects regularly travel between star systems. This realization transforms our perspective from viewing our solar system as an isolated island to understanding it as part of a vast, interconnected cosmic ecosystem. Future generations of astronomers will have access to increasingly sophisticated tools for detecting and studying these cosmic messengers. Each new discovery will add to our growing understanding of how matter, and potentially life itself, spreads throughout the galaxy. 3I Atlas may be just the beginning of a new chapter in human exploration of the cosmos, one where the universe comes to us in the form of ancient travelers from distant stars. The discovery of 3I Atlas opens an unprecedented window into the ancient cosmos, offering humanity its first detailed look at a massive object from another star system. As this colossal interstellar visitor races through our solar system, it carries secrets from a distant world that may have existed billions of years before Earth formed. The data collected during its brief passage will enhance our understanding of planetary formation, the distribution of life's building blocks, and our cosmic heritage. What other ancient messengers await discovery in the depths of space? Share your thoughts below, hit that like button, and subscribe to Future Facts for more incredible cosmic discoveries. Until next time, keep looking up. After 46 years of exploration, Voyager 1 has finally broken through the ultimate barrier, the heliosphere, and entered true interstellar space. But, the data streaming back from 15 billion miles away is completely rewriting everything scientists thought they knew about the void between stars. This isn't the empty darkness we expected. The space beyond our solar system's protective bubble is alive with invisible forces, mysterious structures, and phenomena that challenge our understanding of the galaxy itself. Today, we're exploring 10 groundbreaking discoveries that prove interstellar space is nothing like we imagined. The magnetic field mystery. The first shock hit scientists when Voyager 1's magnetometer detected something completely unexpected in 2012. Instead of finding chaotic, randomly oriented magnetic fields, the spacecraft discovered that interstellar space has a surprisingly organized magnetic structure. Dr. Leonard Berlanga, from NASA's Goddard Space Flight Center, was among the first to analyze these readings, revealing that the interstellar magnetic field runs nearly perpendicular to our solar system's magnetic field. This sharp 90-degree misalignment suggests we're encountering the edge of a massive galactic magnetic domain. The implications are staggering. These aren't local phenomena but galaxy-wide structures that could influence star formation, cosmic ray propagation, and even the evolution of planetary systems. The magnetic field strength measured at 0.4 nanotesla is actually stronger than predicted, indicating that interstellar space contains more organized energy than our models suggested. This discovery fundamentally changes how we understand magnetic field interactions on galactic scales. The cosmic ray bombardment. Crossing the heliopause in August 2012, Voyager 1 immediately encountered a radiation environment that defied all expectations. Dr. Edward Stone, the mission's project scientist since 1977, watched in amazement as cosmic ray levels spiked by 300% almost instantly. These high-energy particles, accelerated by distant supernova and black holes, bombard everything in interstellar space at intensities that would be lethal to unprotected astronauts. The cosmic ray subsystem aboard Voyager detected particles with energies exceeding 100 million electron volts, radiation levels so intense they would fry electronic equipment within months. But here's the most surprising part. The cosmic ray patterns aren't random. Voyager's instruments have measured systematic variations that suggest interstellar space has natural radiation corridors and safe zones. These findings prove our sun's heliosphere acts as a far more effective cosmic ray shield than anyone realized, protecting Earth and our entire solar system from this invisible galactic storm. The plasma wave discovery. Silence doesn't exist in interstellar space. Voyager 1's plasma wave subsystem, designed by Dr. Donald Gurnett at the University of Iowa, has been detecting constant low-frequency oscillations since entering the interstellar medium. These aren't random static, they're organized plasma waves that create what scientists now call the interstellar hum. Operating at frequencies between 2 and 3 kilohertz, these waves indicate that interstellar space is filled with electrically charged particles constantly in motion. Dr. Stella Ocker, a Cornell University researcher, recently analyzed 5 years of this data and discovered that these plasma oscillations change frequency as Voyager moves through different regions. The waves intensify near density boundaries and quiet down in more uniform areas, creating an acoustic map of interstellar structure. This discovery proves that interstellar space isn't a void, but an active medium where plasma waves propagate across vast distances, potentially carrying information about distant stellar explosions, magnetic field reconnections, and other galactic events happening light-years away. The local interstellar cloud. Voyager 1 isn't just floating through empty space, it's actually swimming through what astronomers call the local interstellar cloud. Dr. Priscilla Frisch from the University of Chicago has spent decades studying this region, and Voyager's direct measurements have confirmed her theoretical models. This interstellar cloud extends roughly 30 light-years in all directions around our solar system, and contains about 0.3 atoms per cubic centimeter, which is incredibly sparse by Earth standards but still significantly denser than the cosmic void beyond. The cloud formed approximately 4 to 5 million years ago when multiple supernova explosions carved out a cavity in the interstellar medium. Voyager's instruments have detected the cloud's temperature at around 6,000 Kelvin and confirmed it's moving relative to our solar system at 26 kilometers per second. As we drift through this cloud over the next 50,000 years, it'll gradually affect Earth's climate by modulating the cosmic ray flux that reaches our planet, potentially influencing cloud formation and atmospheric chemistry in subtle but measurable ways. The heliosphere's true shape. Everything we thought we knew about our solar system's protective bubble was, well, wrong. Voyager 1's journey has revealed that the heliosphere isn't the neat comet-shaped structure you might remember from textbooks. Dr. Merav Ofer from Boston University has been leading research using Voyager data, and her team discovered that our solar system's boundary is far more complex and turbulent than anyone predicted. The heliopause, that's the boundary between the solar wind and interstellar medium, varies dramatically in different directions. While Voyager 1 crossed this boundary at 121 astronomical units from the Sun, Voyager 2 encountered it at 119 AU, but in a completely different region with its own distinct characteristics. NASA's New Horizons spacecraft, still approaching this boundary, is providing even more data points that suggest the heliosphere might have a more irregular, possibly even fragmented structure. This discovery has profound implications for cosmic ray shielding and helps explain why the interstellar medium penetrates more deeply into our solar system than models predicted, creating these complex interaction zones where solar and interstellar forces are constantly battling for dominance. The density fluctuations. Interstellar space actually has weather, and Voyager 1 is our very first weather station beyond the solar system. Since 2013, the spacecraft's plasma wave instrument has detected at least 5 distinct density variations in the interstellar medium, each representing a different climate zone in deep space. Dr. Bill Kurth from the University of Iowa analyzed these fluctuations and found that interstellar plasma density can change by factors of 2 to 3 over relatively short distances. The most dramatic shift happened in 2014, when Voyager encountered a density spike that lasted several months, indicating passage through a compressed region possibly created by stellar winds from nearby stars. These variations aren't just random, they actually follow patterns that suggest interstellar space has structure on multiple scales. Some regions are compressed by shock waves from ancient supernovae, while others are rarefied cavities carved out by stellar winds. Voyager's measurements reveal that our local interstellar cloud has internal boundaries and substructures, making interstellar space far more dynamic and organized than the uniform medium astronomers once envisioned. The galactic coordinates. Every measurement Voyager 1 takes is helping scientists build humanity's first three-dimensional map of interstellar space. Dr. Nathan Schwadron from the University of New Hampshire leads the team creating these galactic coordinate systems using Voyager's position as a fixed reference point about 15 billion miles from Earth. The spacecraft's current trajectory takes it toward the constellation Ophiuchus, where it will continue for thousands of years unless it's deflected by gravitational encounters. But Voyager isn't just traveling in a straight line, it's mapping magnetic field orientations, plasma densities, and cosmic ray gradients that, vary by galactic location. These measurements reveal that interstellar space has preferred directions and asymmetrical structures aligned with our galaxy's rotation. The magnetic field Voyager measures points toward the galactic center in some regions and away in others, suggesting complex field line geometries shaped by stellar formation and supernova events over millions of years. This galactic GPS system will eventually guide future interstellar missions, helping them navigate the invisible currents and radiation zones that Voyager is now charting for the first time. The temperature paradox. Interstellar space is simultaneously scorching hot and freezing cold, and Voyager 1 has measured both extremes. The interstellar medium itself reaches temperatures of 50,000 to 100,000 Kelvin, hot enough to vaporize any known material. Yet, Voyager's instruments register near absolute zero temperatures because the particle density is so low that there's virtually no heat transfer. Dr. Gary Zank from the University of Alabama explains this paradox. Individual plasma particles move at tremendous speeds, which means high temperature, but they're so spread out that the spacecraft actually experiences the cold of deep space. Voyager's cosmic ray subsystem has detected temperature variations in different regions of interstellar space, with some areas reaching 200,000 Kelvin, where shock waves from stellar explosions have compressed and heated the plasma. These temperature measurements reveal the energy budget of interstellar space, showing how supernova explosions, stellar winds, and galactic rotation, pump energy into the interstellar medium. Understanding these thermal processes is crucial for predicting how interstellar gas eventually collapses to form new stars and planetary systems. The communication miracle. Keeping Voyager 1 alive and transmitting from interstellar space represents honestly one of NASA's greatest technical achievements. Suzanne Dodd, Voyager project manager at JPL, oversees a mission using 1970s technology to communicate across interstellar distances. The spacecraft transmits with just 23 watts of power, less than a refrigerator light bulb. Yet NASA's Deep Space Network can still detect its whisper-faint signals after they travel for 22 hours at the speed of light. In late 2023, Voyager suffered a critical computer failure when cosmic radiation corrupted its flight data subsystem. Engineers led by Linda Spilker performed digital surgery across 15 billion miles, reprogramming 1970s computer code to bypass damaged memory sectors. The repair took months because every command required a 44-hour round trip for confirmation. By April 2024, they successfully restored communication with all 4 active science instruments. This remarkable resurrection really proves that American engineering from the space race era was built to last, giving us precious additional years of interstellar data from humanity's most distant explorer. The Golden Record's journey. Beyond its scientific mission, Voyager 1 carries humanity's greatest time capsule into eternity. The Golden Record, curated by Carl Sagan and Anne Druyan in 1977, contains sounds, music, and images representing Earth's diversity in 55 languages. Dr. Timothy Ferris, who produced the record, selected Bach, Beethoven, Chuck Berry, and traditional music from around the world. NASA engineers designed the record to survive billions of years in space, with instructions engraved in pure gold showing how to play it and how to locate Earth. The record includes greetings from President Jimmy Carter, UN Secretary General Kurt Waldheim, and children from all around the world. As Voyager travels toward the star Gliese 445, it'll make its closest stellar approach in 40,000 years, passing within 1.6 light-years of this red dwarf. Even after Earth's continents drift beyond recognition and human civilization evolves beyond imagination, the Golden Record will preserve our 1970s snapshot of humanity. Carl Sagan called it a bottle cast into the cosmic ocean, and now that bottle has reached the interstellar sea, carrying our message to whatever intelligence might someday find it drifting among the stars. Voyager 1 has shattered, just about every assumption about interstellar space, revealing a cosmic environment that's structured, active, and far more complex than we ever imagined. From magnetic field mysteries to plasma weather systems, this 1970s spacecraft continues revolutionizing our understanding of the galaxy itself. Voyager proves we live in a protected cosmic oasis, shielded from the harsh radiation of deep space. So, which discovery amazed you most? Drop your thoughts below. If you loved exploring these interstellar revelations, hit that like button, share with space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries. In September 2022, NASA's DART spacecraft successfully slammed into Dimorphos, a small asteroid moon, marking humanity's first attempt at planetary defense. The mission was designed to slightly alter the asteroid's orbit, proving we could deflect potentially dangerous space rocks. But what happened next shocked scientists worldwide. Instead of the predicted minor course change, Dimorphos experienced dramatic transformations that revealed stunning secrets about asteroid composition and behavior. The aftermath created a cosmic spectacle visible from Earth, fundamentally changing our understanding of these ancient space wanderers and our ability to protect our planet. The perfect bullseye. The moment of impact arrived with surgical precision. At 7:14 p.m. Eastern Daylight Time on September 26, 2022, DART struck Dimorphos at 6.14 kilometers per second, releasing energy equivalent to 3 tons of TNT. Mission Director Nancy Chabot watched from Johns Hopkins Applied Physics Laboratory as telemetry confirmed the spacecraft had hit its target dead center. The refrigerator-sized probe had traveled 11 million kilometers over 10 months to reach this 160-meter-wide asteroid moon, orbiting around its larger companion Didymos. Ground-based telescopes immediately began tracking the aftermath, with astronomers worldwide coordinating observations. The impact created a spectacular debris plume that extended thousands of kilometers into space, visible as a bright tail reminiscent of a comet. Within hours, measurements confirmed DART had exceeded all expectations. Instead of the predicted 73-second orbital period change, Dimorphos was slowing down by an astounding 11.5 minutes per orbit. This dramatic alteration meant the mission had been roughly 25 times more effective than the minimum success threshold, suggesting asteroid deflection might be far easier than previously thought. The debris cloud mystery. The impact unleashed a cosmic fireworks display that continued for months. LICIACube, a small Italian satellite deployed by DART, captured stunning close-up images of the collision aftermath, showing massive boulders and dust streaming away from Dimorphos at high velocity. Dr. Elisabetta Dotto from INAF Astronomical Observatory of Rome analyzed the footage, revealing that some debris chunks were larger than cars, ejected at speeds exceeding 500 meters per second. The debris cloud evolved dramatically over time, initially forming a double-tail structure that confused astronomers. Ground-based observations from the Lowell Observatory showed the tail stretching over 10,000 kilometers through space, making Dimorphos temporarily appear comet-like. Most surprisingly, the debris pattern suggested Dimorphos wasn't a solid rock, but rather a loosely bound rubble pile held together primarily by gravity. This discovery revolutionized understanding of asteroid composition, indicating that many near-Earth asteroids might be fragile collections of smaller rocks, rather than monolithic stones. The extended debris emission also meant the orbital change would continue for weeks, as material kept streaming away from the asteroid. The Hubble revelations. Hubble Space Telescope observations revealed phenomena that no one had predicted. Dr. John Yang Lee from Planetary Science Institute led the analysis of Hubble's unprecedented views of the impact aftermath. The space telescope detected boulder-sized debris ejected from Dimorphos traveling at various speeds, creating multiple distinct tail structures that evolved over time. Most remarkably, Hubble observed the debris cloud brightening and dimming in 11.9-hour cycles, matching Dimorphos's rotation period and suggesting ongoing material ejection synchronized with the asteroid's spin. The observations revealed that impact debris continued streaming away from Dimorphos for several weeks after the collision, far longer than models predicted. Spectroscopic analysis showed the ejected material contained silicate minerals and metallic compounds consistent with primitive asteroid composition. The debris patterns also indicated that DART had struck during Dimorphos's northern hemisphere winter, when that region faced away from the sun. This timing may have enhanced the impact's effectiveness by hitting material that was colder and potentially more brittle. Hubble's data proved that asteroid impacts create complex, long-lasting debris systems that could pose navigation hazards for future spacecraft missions. The James Webb discovery. The James Webb Space Telescope made an unexpected discovery that really changed everything scientists thought they knew about the impact. Dr. Christina Thomas from Northern Arizona University actually used Webb's infrared capabilities to look right through the debris cloud and observe Dimorphos directly. The observations showed that the asteroid's surface temperature shot up by about 40 degrees Celsius after the impact, which, points to massive internal structural changes. Even more surprising, Webb detected water vapor and organic compounds in the material that was thrown out, stuff that shouldn't really exist on such a small, airless body. The infrared spectra also showed hydrated minerals being exposed to direct sunlight for the first time, which suggests Dimorphos contains significant amounts of water ice locked away inside its structure. Most surprisingly, Webb observed these periodic thermal emissions from the impact crater that pulsed every few hours, possibly hinting at ongoing subsurface processes, or maybe just structural settling. The telescope even picked up traces of carbon-based molecules, which could represent some of the most primitive organic matter in our entire solar system. All these findings suggested that small asteroids like Dimorphos might actually preserve pristine materials from the early days of the solar system's formation, making them incredibly valuable scientific targets for future sample return missions. The seismic surprise. The impact triggered some pretty unexpected seismic activity throughout the Didymos binary system. Dr. Derek Richardson from University of Maryland used computer simulations to model how DART's impact energy moved through both asteroids. The collision sent shockwaves through Dimorphos that actually got transmitted to its larger companion, Didymos, through gravitational coupling, kind of creating a cosmic tuning fork effect. Ground-based radar observations from Arecibo Observatory's successor facilities picked up on subtle changes in Didymos's rotation rate, showing that the bigger asteroid had also been affected by the impact. The seismic energy ended up causing landslides and boulder movement across both asteroid surfaces, reshaping their geological features in real time. Most dramatically, it looks like the impact actually changed Dimorphos's internal structure, making it less spherical and more elongated as gravity redistributed all that loosened material. Light curve analysis showed that the asteroid's brightness variations changed a lot, which means there were permanent alterations to its shape and surface features. This kind of seismic coupling between binary asteroids had never been seen before, and it suggests that deflecting one member of a binary pair could have some pretty unpredictable effects on both objects. This discovery has major implications for future planetary defense strategies, especially when it comes to binary asteroid systems. The unexpected acceleration. Months after the impact, Dimorphos started showing some really bizarre behavior that just didn't fit any predictions. Dr. Andy Rivkin from Johns Hopkins Applied Physics Laboratory noticed that instead of things settling down, the asteroid's orbital period kept changing, and at an accelerating rate too. By February 2023, Dimorphos was actually orbiting Didymos 33 minutes faster than before the impact, which is nearly 3 times the immediate post-impact change. This ongoing acceleration suggested that DART's impact had set off processes that continued for months afterward. Computer models showed that continued mass loss from the asteroid was creating a kind of rocket effect, where the ejected material acted like a weak but persistent thruster. Thermal analysis revealed that solar heating was causing volatiles buried inside Dimorphos to sublimate and escape, carrying dust and small rocks along with them. The Yarkovsky effect, where absorbed and re-radiated sunlight creates these tiny thrust forces, was also playing a role in the orbital changes. Most remarkably, the asteroid seemed to be losing density, becoming more porous as internal voids expanded. This discovery means that asteroid deflection missions might have long-term effects lasting years or even decades, fundamentally changing how we need to plan and execute planetary defense strategies. The hidden water ice. The most shocking discovery came from analyzing the spectral signatures of ejected debris. Dr. Ian Wong from the Space Telescope Science Institute identified clear evidence of water ice within Dimorphos's interior structure. The impact had excavated material from depths of several meters, exposing subsurface ice that had been hidden for billions of years. This finding, honestly, revolutionized understanding of near-Earth asteroid composition, suggesting that many small asteroids retain water from the early solar system's formation. The ice discovery explained why DART's impact was so much more effective than predicted. Water ice sublimates when heated, creating gas pressure that helped blow material away from the asteroid. Spectroscopic measurements showed the water ice was mixed with silicate dust and organic compounds, creating a primitive mixture resembling comet nuclei. Interestingly, the ice appeared to be distributed throughout Dimorphos, rather than concentrated in specific regions, indicating the asteroid formed in the outer solar system where water could freeze before migrating inward. This discovery has profound implications for asteroid mining and space exploration, as water-rich asteroids could provide fuel and life support for future deep space missions. The finding also suggests that impacts on similar asteroids might release water vapor visible from Earth. The crater that wasn't there. Perhaps the most puzzling aspect of DART's impact was what didn't happen. No clear crater formed. Dr. Sabina Radican from the University of Bern led computer simulations, trying to understand why the expected impact crater never appeared. High-resolution images from ground-based telescopes and LISIACube showed that instead of a well-defined crater, DART had created a broad depression surrounded by redistributed material. The lack of a distinct crater suggested that Dimorphos's surface consists of extremely loose material, more like a pile of sand than solid rock. Impact modeling indicated that DART's energy was absorbed by compacting and ejecting surface material rather than excavating a traditional crater. The missing crater meant that most impact energy went into accelerating debris rather than breaking rock, which honestly explains the mission's unexpected effectiveness. Comparative analysis with lunar and asteroid craters showed that Dimorphos represents a new category of ultra-low-density targets that respond differently to impacts. This discovery has major implications for future kinetic impactor missions, suggesting that loose rubble pile asteroids might be easier to deflect than previously thought. The absent crater also means traditional crater counting methods for determining asteroid ages may not apply to such objects. The Global Observation Campaign. The DART impact triggered the largest coordinated asteroid observation campaign in history. Dr. Nicholas Moskovitz from Lowell Observatory coordinated observations from over 100 telescopes worldwide, creating an unprecedented data set of the impact's effects. Amateur astronomers contributed crucial observations, with backyard telescopes detecting the debris plume and orbital changes from millions of kilometers away. The European Space Agency's ground-based telescopes tracked debris evolution for months, revealing how impact ejecta spreads through interplanetary space. Radio telescopes detected subtle changes in the asteroid's thermal emissions that revealed internal temperature variations. The global campaign discovered that Dimorphos's brightness varied significantly after impact, indicating major surface changes and ongoing material redistribution. Photometric analysis showed the asteroid's color changed as fresh material from its interior was exposed to space. Most remarkably, some observatories detected secondary debris clouds forming weeks after the initial impact, suggesting ongoing structural collapse within the asteroid. This worldwide collaboration demonstrated that planetary defense requires international cooperation, and showed how citizen scientists can contribute to major space missions. The campaign also proved that relatively small telescopes can make crucial discoveries about asteroid behavior. The future of planetary defense. DART's success has revolutionized planetary defense strategy and opened new possibilities for protecting Earth. Dr. Lindley Johnson, NASA's planetary defense officer, announced that the mission exceeded all expectations, proving that kinetic impactors can effectively deflect dangerous asteroids. The 33-minute orbital change means similar missions could alter asteroid trajectories with years or even decades of advance warning. ESA's Hera mission, launching in 2024, will conduct detailed investigations of the impact site and crater, providing crucial data for future deflection missions. The discovery that many asteroids are loosely bound rubble piles suggests deflection might be easier than expected, but also raises questions about structural stability after impacts. NASA is now developing larger kinetic impactors and considering multiple impact strategies for particularly dangerous asteroids. The water ice discovery has sparked interest in dual-purpose missions that could both defend Earth and harvest resources for space exploration. International cooperation on planetary defense has strengthened, with multiple countries contributing telescopes and expertise to asteroid tracking networks. DART proved that humanity has the technology to defend our planet, transforming planetary defense from science fiction into engineering reality. The mission's success ensures that future generations will have the tools to prevent cosmic catastrophe. DART's impact on Dimorphos proved humanity can successfully defend Earth from asteroid threats, but the aftermath revealed surprises that, honestly, revolutionized our understanding of these ancient space rocks. From water ice discoveries to ongoing orbital changes, the mission exceeded every expectation and opened new frontiers in planetary science. The 33-minute orbital shift demonstrated that asteroid deflection is not only possible, but remarkably effective. Which DART discovery amazed you most? Share your thoughts below. If you loved learning about this historic space mission, hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries. Since 2016, NASA's Juno spacecraft has been peering beneath Jupiter's beautiful but deceptive cloud layers, uncovering secrets that challenge everything we thought we knew about the solar system's largest planet. What mission scientists discovered deep within Jupiter's atmosphere defies explanation. A mysterious central storm system unlike anything found elsewhere in the universe. The data streaming back from Juno's sensors reveals that Jupiter isn't just a giant ball of gas, but a world harboring terrifying forces and unexplained phenomena that could reshape our understanding of planetary formation itself. The mysterious central storm discovery. Deep within Jupiter's core lies a discovery that has left planetary scientists speechless. Juno's microwave radiometer penetrated 350 kilometers below the cloud tops and detected what appears to be a permanent central vortex spanning thousands of kilometers across. Unlike the Great Red Spot or other visible storms, this deep atmospheric feature shows no signs of the typical cyclonic rotation patterns found elsewhere on Jupiter. Dr. Scott Bolton, Juno's principal investigator, describes it as a hurricane frozen in time, a massive atmospheric disturbance that appears to have remained unchanged for potentially millions of years. The storm system generates electromagnetic pulses that interfere with Juno's instruments, creating data gaps that suggest something far more complex than simple atmospheric circulation. Most disturbing is the storm's perfect geometric structure. It forms concentric rings with mathematical precision that defies known meteorological processes. The central vortex appears to extend all the way down to Jupiter's metallic hydrogen core, creating a direct channel between the planet's surface storms and its deepest interior regions. The beginning of the mission. Juno launched on August 5, 2011, beginning a 5-year journey to reach Jupiter and unlock the secrets of the solar system's formation. The spacecraft was designed with a unique polar orbit that would allow it to study Jupiter's interior structure without being destroyed by the planet's deadly radiation belts. Lockheed Martin built the titanium-armored probe to withstand radiation levels 1,000 times stronger than those that would kill a human instantly. The mission's primary goals included mapping Jupiter's gravitational field, studying its atmospheric composition, and determining whether the planet has a solid core. NASA scientists equipped Juno with 9 sophisticated instruments, including a JunoCam for public outreach and scientific imaging. The spacecraft's 3 massive solar panels make it the most distant solar-powered probe ever launched, generating electricity from sunlight 25 times weaker than that reaching Earth. After traveling 2.8 billion kilometers, Juno successfully entered Jupiter's orbit on July 4, 2016, beginning what would become one of the most revolutionary planetary exploration missions in history. Jupiter is the world of chaos. Jupiter's atmosphere operates on a scale of violence that dwarfs anything found on Earth. Wind speeds reach 640 kilometers per hour, nearly twice as fast as the strongest hurricanes ever recorded on our planet. The atmospheric bands that give Jupiter its distinctive striped appearance are actually jet streams containing more energy than all of Earth's weather systems combined. Dr. Andy Ingersoll from Caltech discovered that Jupiter's storms can maintain their intensity for centuries, with some features persisting longer than human civilization has existed. The planet's rapid 9.9-hour rotation creates Coriolis forces so powerful they tear apart smaller storm systems while strengthening larger ones. Temperature variations between different atmospheric layers create vertical wind shears that would instantly destroy any Earth-based aircraft. Most shocking is the discovery of thermal towers, massive columns of superheated gas that erupt from deep within Jupiter's interior, carrying energy equivalent to multiple nuclear explosions every second. These thermal plumes create the pop-up clouds that appear suddenly at atmospheric boundaries, representing eruptions of material from depths of over 100 kilometers below the visible cloud deck. Io, the volcanic moon. Io, Jupiter's innermost large moon, represents a world that's literally being torn apart by gravitational forces. This sulfur-covered hellscape hosts over 400 active volcanoes, making it, well, the most geologically active body in the solar system. Dr. Rosalie Lopez from JPL has cataloged volcanic eruptions on Io that blast material 500 kilometers into space. That's high enough to reach from Earth's surface all the way up to the International Space Station. Jupiter's immense gravity, along with the gravitational tugging from Europa and Ganymede, creates tidal flexing that generates enough internal heat to actually melt Io's rocky interior. The moon's volcanic activity pumps 1 ton of material per second into Jupiter's magnetosphere, creating a plasma torus that, feeds the planet's radiation belts. Some of Io's volcanic plumes reach temperatures of 1,800 degrees Celsius, that's hot enough to melt copper, while ejecting sulfur dioxide snow that gives the moon its distinctive yellow and orange appearance. Juno's observations reveal that Io's volcanic activity directly influences Jupiter's auroras, creating an electrical connection between the moon and the planet that generates 5 million amperes of current flowing through space. Research on Jupiter's magnetic field. Jupiter's magnetic field represents one of the most powerful and complex magnetic environments in the solar system. Generated by electrical currents in the planet's metallic hydrogen core, the field extends over 1 million kilometers from Jupiter's surface, so large it would appear 5 times the size of the full moon if you could actually see it from Earth. Dr. Jack Connerny from NASA Goddard leads research showing that Jupiter's magnetosphere contains enough energy to power human civilization for millions of years. The magnetic field traps charged particles from the solar wind, creating radiation belts that are 10,000 times more intense than Earth's Van Allen belts. Most mysteriously, Juno discovered that Jupiter's magnetic field has an asymmetric structure with a distinct northern magnetic anomaly, a feature that really shouldn't exist according to traditional magnetic field models. The field appears to be generated by shallow flows in the metallic hydrogen layer, rather than by deep convection processes as previously assumed. This discovery suggests that Jupiter's interior structure is far more complex than simple models predict, with multiple layers of conducting fluids creating a dynamo system unlike any other planet we've studied. Juno mission peaks under Jupiter's surface. Juno's gravitational measurements have, honestly, revolutionized our understanding of Jupiter's internal structure by revealing what actually lies beneath those swirling clouds. The spacecraft's precision tracking detected gravitational anomalies indicating that Jupiter has a fuzzy or dilute core, rather than the distinct, solid center that scientists had expected. Dr. Tristan Guillot from Observatoire de la Côte d'Azur analyzed the data, showing that heavy elements are mixed throughout Jupiter's interior instead of being concentrated in a central core. This partially dissolved core extends outward for thousands of kilometers, containing between 7 and 25 Earth masses of rocky material distributed through the planet's metallic hydrogen region. The discovery suggests that Jupiter suffered a massive collision early in its formation, an impact so violent it scattered core material throughout the planet's interior. Microwave soundings reveal that Jupiter's ammonia concentration varies dramatically with depth, creating distinct atmospheric layers that trap and release gases in complex cycles. The planet's interior rotates as a solid body down to depths of 3,000 kilometers, below which differential rotation creates shearing forces that generate the observed magnetic field patterns. Jupiter's formation and composition. Jupiter's formation story has been, completely rewritten by Juno's discoveries about the planet's water content and internal structure. Dr. Chung Lee from UC Berkeley found that Jupiter actually contains about 3 times more water than expected, with concentrations that, interestingly, vary dramatically between different atmospheric regions. The uneven water distribution suggests that Jupiter formed through core accretion rather than gravitational collapse, meaning it slowly built up from solid materials before capturing gas from the solar nebula. Heavy elements make up between 3 and 9% of Jupiter's total mass, far more than previous models predicted, which indicates the planet accumulated significant amounts of rocky planetesimals during its formation. The discovery of phosphine gas in Jupiter's upper atmosphere provides evidence of vertical mixing, which transports material from deep interior regions where the gas forms under extreme pressure. Isotopic ratios measured by Juno even suggest that Jupiter migrated inward toward the Sun during its early history before moving back to its current position, a grand tack model that helps explain the architecture of our entire solar system. This migration scattered asteroid belt material and prevented super-Earth formation in the inner solar system. Jupiter as Earth's protector. So, Jupiter actually serves as Earth's gravitational guardian, deflecting potentially catastrophic asteroids and comets away from the inner solar system. According to computer simulations by Dr. Kevin Grazier, without Jupiter's immense gravity, Earth would be bombarded by impacts 1,000 times more frequently, making complex life, well, virtually impossible. The planet's orbital resonances, create asteroid families and gaps in the asteroid belt, which prevents small rocky bodies from spiraling toward Earth. During the early solar system, Jupiter's migration scattered icy comets from the Kuiper belt, and many of those actually delivered the water that fills Earth's oceans today. The planet also captures interstellar objects entering our solar system, like asteroids from other star systems that could otherwise pose unpredictable threats to Earth. Recent studies show that Jupiter's gravitational influence extends beyond Neptune's orbit, affecting the trajectories of long-period comets that originate in the Oort cloud. But here's the thing. Jupiter occasionally sends objects toward Earth as well, since its gravity can perturb comet orbits and redirect them into the inner solar system. So, this double-edged protection means Jupiter both shields and sometimes threatens Earth, maintaining a delicate balance that has allowed life to flourish on our planet. The Great Red Spot Mystery. The Great Red Spot has been shrinking for over 150 years, and Juno's close-up observations are finally revealing why this iconic storm may be slowly dying. Dr. Amy Simon from NASA Goddard discovered that the storm has lost 50% of its width since the 1800s, and it continues shrinking at an accelerating rate. Juno's infrared spectrometer found that the Great Red Spot extends about 300 kilometers deep into Jupiter's atmosphere, much deeper than any hurricane on Earth, but actually shallower than expected for such a long-lived feature. The storm's distinctive red color comes from complex organic compounds created when ammonia and hydrogen sulfide are exposed to ultraviolet radiation from the sun. Wind measurements show that the storm's outer edges rotate faster than its center, creating shearing forces that may be gradually tearing the vortex apart. Most mysteriously, the Great Red Spot sometimes changes color from deep red to pale orange, which suggests chemical reactions are happening within the storm system. Computer models suggest the storm may completely disappear within the next 50 years, ending a 300-year-old atmospheric feature that has served as Jupiter's most recognizable landmark. The atmospheric river's discovery. Juno's microwave radiometer uncovered a previously unknown feature that might be Jupiter's most important atmospheric discovery: massive atmospheric rivers flowing beneath the visible cloud layers. These invisible currents transport ammonia and water vapor across thousands of kilometers, working like conveyor belts that redistribute heat and chemicals throughout Jupiter's atmosphere. Dr. Karen Dewar from the Weizmann Institute identified these deep atmospheric streams using radio emissions that can penetrate Jupiter's thick clouds. The atmospheric rivers flow at depths of 100 to 200 kilometers below the surface, carrying 10 times more material than all of Earth's atmospheric circulation combined. These hidden currents help explain how Jupiter's bands maintain their distinct chemical compositions, even with all the planet's turbulent mixing. The rivers seem to connect polar cyclones with equatorial jet streams, creating a global circulation pattern that operates independently of surface weather. Most remarkably, these deep atmospheric flows may be directly connected to Jupiter's metallic hydrogen core, suggesting that the planet's weather systems extend all the way to its center. This discovery really shows that Jupiter's atmosphere is a three-dimensional system, way more complex than the simple layered structure scientists used to assume. Juno's revelations about Jupiter have, honestly, shattered our understanding of the solar system's giant. From mysterious central storms to atmospheric rivers flowing beneath the clouds, Jupiter harbors secrets that challenge fundamental theories about planetary formation. The discovery that our cosmic protector contains a partially dissolved core and complex interior dynamics proves there's still so much to learn about our celestial neighborhood. So, which Jupiter mystery fascinated you the most? Share your thoughts below. If you enjoyed uncovering these incredible planetary secrets, go ahead and hit that like button, share with fellow space enthusiasts, and subscribe to Future Facts for more mind-blowing cosmic discoveries.